And the next speaker is Wang Yu, who will give, from ICRANet, who will give a speech about the role of binary system 1708-17.
Okay, I'm going to give a talk on this sketching, this gamma ray burst 1708, 17A, and the kilonova by data and binary systems on behalf of our group. So we know this GRB has been observed by a lot of satellites, more than 30. So it provides us the best data ever to do the analysis and to infer the physical system. So this will be my first part. Then my second part is about the binary stars. We are working on a different way, but we want to see, is there a system, binary system can produce so low energy gamma burst and the kilonova. So let's start from the data part. Because since we have a lot of data, especially the optical and infrared data, so let's see how far we can go with the data. Because the detailed optical and infrared data give us an opportunity to explore the kilonova in an observational-oriented way. So we want to start without employing any physical model, existing physical model. Let's just see the data, focus on data, and let the data guide us as far as possible. If the data is not enough, then we make some simplest assumption based on what we have observed. So first, let's have a general view of this kilonova and the GRB. So we start from the left side, plotted in linear. And we have this GRB 1707, 1708, 17A with the blue points. It has two spikes. And it has very low luminosity, less than 10 to 47 erg per second. And above, we show one typical short GRB 050, 09, 0510, and the two other kilonovae, which all of them are above, all those magnitudes above this gravitational wave kilonova GRB. And also, let's see the GeV emission, the GeV emission. There's only one point at the red point. It has an upper limiter, and the upper limiter is much lower than the GeV emission observed in GRB 09 of 10. Also, the X-ray plotted in green is very different, because for those normal kilonovae and the short GRBs also much higher, and we saw the X-ray emissions, but this one, the X-ray is absent. But the X-ray starts to arise at about 10 days. So we have these very deep green points on the right bottom side. Also for the optical is lower than those typical ones. So only the infrared, which indicates it's a kilonova, coincides with other kilonovae. So the conclusion is this kilonova, the kilonova part is similar to other kilonovae, but the GRB is quite different from an observational point of view. So since it has two spikes in the prompt emission, let's see the spectra first. This is the first one, which has almost 1 second duration, and it is fitted by a cutoff power law, and the cutoff energy is quite low, about 200 keV. And the second one is quite special because it can be fitted by a black body. The black body temperature is 11 keV. We know for the usual GRBs, always for some GRB, we see the thermal emission in the very beginning, then it follows the non-thermal emission. But this one, first we have the non-thermal, then it comes the thermal. Next, this is the very good data collected by the kilonova .space website maintained by James and thanks. And after some corrections of the absorption and the different photometric systems, we have this beautiful plot on the right side. This plot has 655 points and is binned by these 16 time intervals. From 0.5 day to 16 days, we see from this plot in the beginning, the black body is presented by this thick line, can very well fit the data. And it starts to deviate from about 7 days, generally speaking, because the infrared data can still be fitted by a very well black body, but the optical deviates. So we have a very almost perfect black body in the beginning, before 7 days. Then the power law component starts to appear. Later, I just talk about before 70 days, it's the opaque region, then the transparent region for simplicity. Then by fitting this black body spectra, also we know the distance of this object. We can infer the luminosity, also we can compare the radius. So we have this luminosity decreasing from 10 to 42 per second to 10 to 41 per second. Also the temperature decreases from 1 eV, so in the optical, to 0.1 eV in the infrared. Then the radius increases from 10 to 14 centimeter till 10 to 15 centimeter within these 10 days. Then the simplest thing we can do is to infer the velocity, because we have how the radius is changing by the time. This answers one question raised by in the first talk. I remember. So we have this velocity. The velocity is decreasing. You see from this plot from 0.2 c to 0.1 c. This is somehow against our intuition, because we always assume there is a neutron-star black hole, some compact object in the center, and it emits its rotational energy. So in these days, in principle, the velocity should not decrease so much. But also we know this is the velocity of the photosphere, not the velocity of the system of the expander. So now, since we have this so good kind of data, and we have our results during this 0.5 to 16 days, let's see if we trace back the data, what can we see? Starting from the power law that we found, first is for the Lorentz factor gamma. We know the gamma decreases as a function of the radius, laboratory radius, as minus 1.17, and as the moving temperature, because this system, since this system is moving not so much relativistically, so it is safe to assume that the Lorentz factor and the moving temperature decreases as in the comoving frame. So the law we found should also exist in the comoving frame, we assume. And also we see this temperature decreases as R minus 0.9. This is very close to adiabatic temperature decreasing, because adiabatic value is -1. So this is some modified adiabatic, it can be. So then we do all this relativistic numerical computation from the equal arrival time surface, which is constructed by the photons arriving the observer at the same moment. And numerically speaking, it is composed of a lot of small areas, and each small surface has different velocity, different temperature, with different speed also. Then those color, the top figure shows the example of 3 equal arrival time surface, and the bottom figure, those colorful lines are each small elements, and the total one is a gray color, thick gray, the total one. And the black points, the black line is the effective temperature, because from observation, always we fitted by a black body. This is just one example. So if we trace back, because since we have observed the thermal temperature at the second spike, so we want to trace it back, this thermal expander, to the first second. but not the 0 second, the first second, because we cannot trace it to the very beginning by this very simple law. Then we found the luminosity. When you see the blue line is a bolometric luminosity, and the red points, those red points are the Fermi GBM data, and from 10 keV to 1000 keV. And also we have this thick red line dropping corresponds to the model because it found this expander, how this gamma rate is. So we found that partially it coincides the data, but it is a little higher in the very beginning, in the 0.15 second. And also we can see the X-ray. We plotted in the Swift exact band from 0.3 to 10 keV, the green line. The green line drops before 100 seconds. This gives a possible explanation of why we missed the X-ray, because it drops too early, and the Swift satellite started to observe at 10 to 4 seconds. We can see here. Then is the UV, optical, and the infrared data, because we take these 3 bands, the U band, the R band, and the K band, for example. There is no surprise that we can fit it so well, because we fit the spectra, and we got those power laws. And here is the light curve. And also we found the correspondence. In the light curve, you can see the red line is the R band, optical R band, because from the spectra we saw the transparency starts from a few days, so the fitting does not perfectly well in a few days. But the green line is the infrared. The infrared is always okay. Now for this system, we traced back to the first to 1 second. The velocity at 1 second is equal to c. The gamma Lorentz factor is almost 10, so it's minor relativistic. And the temperature is at keV, close to what we found from the spectra around 10 keV, but a little lower. So our current result shows that our simplest computation does not involve any free parameter. And it is already capable to show the potential of fitting the gamma ray, UV, optical, and infrared data together, and also to explain the missing of the X-ray. But it has a little higher luminosity in the very beginning, 0.5 seconds, and the temperature cannot like 20% lower than the observed value. But this result is from this so simple model. It's not so reality, because in reality we have the acceleration in the very beginning. By this we need to impose a lot of free parameters. So if we have such an increasing acceleration part in the beginning, we will start with a very small radius with low velocity. So we will maintain this small radius for a long time. And since we have a small radius, we will have higher temperature and a lower luminosity. So it's possible to fit the data better, even to fit very well. And also we are very ambitious to see, because we have the first spike of this GRB, which is non-thermal. So can this thermal expander also interpret this non-thermal observation? And this is one example, though we did not fit it perfectly. So if from the data fitting bureau, we always take a time interval, then we do the data fitting. So if the data fitting takes a time interval in which the temperature evolves rapidly, the spectra, here is an example of spectra in the, I put some dotted lines here, the spectra within the Fermi GBM energy range from 8 keV to 1 MeV. And we found that it shows a cutoff power law. You see the cutoff of energy is around 200 keV. And then the power law starts. The index, the photon index of this power law part depends on how the velocity, how the temperature changes dt. So also it is possible if we want to do further analysis. Okay, so this is a very simple tracing back. So if we say that this thermal expander is composed of a lot of different layers with different velocity. So we can compute in another way directly from the data points the velocity of each layer, because we assume that each layer keeps the kinetic energy almost constant, because also from observation we know radiation is little comparing to the kinetic energy. So we have also these velocity drops from 0.3c to 0.1c. And from the fitting of this is the Gaussian process regression, we found that the velocity finally goes to almost a constant 0.12c. Then from a very simple formula of the diffusion, because when we have the velocity of the layer, when we have the emission time of this layer, because we take each time being as one layer with velocity more than v. Then, so we can compute the mass with velocity more than v. Now here I show two lines. The blue one I consider a constant opacity as 10 centimeter square per gram. And the green one is the opacity depending on the temperature, because also we have the temperature of each time beam. So we found that and these two lines, they coincide in the beginning, which means the total mass of this system is around 10 to -2 solar masses. This is consistent with all the previous models and the simulations. But the distribution can be different. The first one has a distribution can be fitted by a polar like a velocity -4, which is comparable to all the models. But the second one, the green one, if the opacity depending on the temperature, that we have less mass with the high velocity, because it's a very steep polar with the index -7. Okay, but this mass we got of 10 to -2 highly depends on the opacity. So if we have a higher opacity, we can decrease this mass, the total mass maybe to 10 to -3. If we have a lower opacity, surely we need to have a very high mass. So this is the seen from data. Then let's see the binary system. Because this GRB, as we said, it's a very strange one. It has so low isotropic energy, it has very low luminosity. So there are two ways to overcome it. The first is to establish a very fine structure of the radiation geometry. The second one is let's find a system in the nature produced by the merger of the two compact stars and release low energy. And we have typically this black hole, neutron star, white dwarf, and they can all these combinations. But here, finally, we choose the white dwarf and the white dwarf, and we have the reasons. But here, let's first forget about gravitational wave, because this system cannot produce gravitational wave. I will show later. For the white dwarf merge, it produces a magnetic field after the merge, about 10 to 10 Gauss. And from this 10 to 10 Gauss, and also we know the radius of 10 to 9 centimeter, for example, we can compute all the magnetic energy stored in these surroundings. So the energy is in the order of 10 to 46 erg. And this energy, also we know that if the speed of the light, if the energy released in 0.1 second, then luminosity is similar to merely released in 0.1 second. The luminosity can be 10 to 47 erg per second, which is quite similar to prompt emission. This is the plot of the gravitational wave from the white dwarf. The frequency of the white dwarf merge is quite low. We see the left upper, the green line. So it is outside the detection range of the advanced LIGO. But here, let's first forget about the gravitational wave, just focus on how this system produce a kilonova and with a very low energy GRB. And we did the first simulation of two white dwarfs. They start from T0, and start to collide and to merge together at 100 seconds, and finally it reaches almost a stable system at 500 seconds. And during this evolution, there are some materials, some mass are ejected unbounded. So from this picture, we have the blue points with the mass finally will fall back. It's bounded mass, and the red ones, but very few. Red ones with the 10 to minus 3 solar mass finally will go out as ejector. This mass has initial velocity 10 to minus 2c, but lately it can be accelerated by the fallback radiation to 0.1c. The data and to infer what is the evolution of this kilonova system. And we found that the photosphere velocity is decreasing, and it's decreasing faster actually. And also, when we explore further the data, tracing back the temperature and the velocity found during this opaque region, tracing it back to the first second, we found that this very simple, just a thermal expander can interpret the data from the gamma ray, X-ray, UV, all the way to the infrared. Also, the mass, so third one is the mass density profile. We obtain the mass density, which is consistent with the simulation and the models. The second conclusion is from the binary system that the white dwarf merge can provide the energy which suits the observation and the prompt emission. And the optical and the infrared emission comes from the kilonova ejector, which is heated by the fallback of the white dwarf. And the X-ray emission, the energy is also from the fallback, but it was not transparent before 108 days because of the opacity from the boundary ionization, but lately it drops. It becomes transparent and it drops. Okay, thank you. Because we always consider there is a synchrotron happening for all the time. Just because the synchrotron occurs inside the ejector at a small radius than the kilonova ejector. So just before 100 days, the synchrotron photons are absorbed by the ejector. But later, the transparency becomes small, then the synchrotron photon can escape from the system. But always there's a synchrotron happening.
Can you show your simulation of the white dwarf merger? So, what is the frequency of this system? What are they are consistent with the frequency of the gravitational wave emitted or no?
The frequency, see this green line.
Okay, so you achieve these frequencies with this in this system. Okay, because they are less gravity. Okay, so you can do it. Okay, thank you.
You said that the mass energy profile is inferred assuming thermal diffusion. Is that the only way that you know in order to get that information, or what you're trying to do?
First, I consider two ways. Because one is from the diffusion, another is from the transparency. But also, I can consider something is always very thick. Then we are observing this, but it becomes transparent and transparent, like the supernova. We are seeing the layers inside and inside. And this is one way. Another way is consider this diffusion. But they gave very similar result, very similar result.
No more to ask on that. Thank you very much.